Welcome to the 2025 AIME 1 problem series. In this video, we're going to be doing problem 8, which is a complex geometry problem. Let k be a real number such that this system is satisfied, and it has exactly one complex solution z. The sum of all possible values of k can be written as m over n, where m and n are relatively prime positive integers, and we want to find the sum of the numerator and the denominator. Well, here, this is the complex plane, and this is the real axis, and this is the imaginary axis. And so the variables we are going to use are going to be b for the imaginary axis and a for the real axis. Okay, so let's go ahead and try and see what we can get from the first equation. So what we're going to do is we're going to let z equal a plus bi. Okay, and let's see what we can get from the first equation. So we have 25 plus 20i minus z, which is the same thing as a plus bi. And we know that the magnitude of this equals 5. So another way to rewrite this is 25 minus a plus 20 minus bi, and this equals 5. And so we know that the formula of a magnitude is this basically translates to 25 minus a squared plus 20 minus b squared equals 5. Since this is essentially distance, we can square both sides and get the a formula that looks very similar to a 2D geometric figure, and that is a circle. And so, oops, I messed up here. So this actually shouldn't be squared on the inside, but rather squared on the outside. And then obviously, since these are squared, it doesn't matter what order we arrange them in. So this is pretty much equivalent. And this looks like a circle that has a center at 25, comma 20. So I would assume like maybe right there is where we can say this circle has its center. And it has a radius of 5. So this would seem accurate. Yep. Okay. Yeah. So now let's try and see what we can get from the second equation. So the first equation, we figured out that the first equation is a circle. So let's see what the second equation turns out to. Okay. Well, again, we can do the same thing. We can write, since z equals a plus bi, we have the magnitude minus 4 minus k, a plus bi minus 3i minus k. Okay, and then here we obviously know that k is a real number, so this is equivalent to writing a minus 4 minus k plus bi is equal to magnitude of a minus k plus b minus 3i. And so now we can write it in terms of distance. And to save a step, I'll go ahead and square both sides so that we don't have a square root. So it should look like this. And obviously, we can go ahead and expand it out. So I would think of this as a minus 4 plus k squared. And then this would be able to expand as such. So And then we have 4 plus k squared plus b squared equals a squared minus 2ak plus k squared. Then we have b squared minus 6b plus 9. And then I'll go ahead and just simplify everything once more. So we get negative 8a minus 2ak plus 16 plus 8k plus k squared plus b squared. And then on the right side, we have everything is the same. And so here it is a lot easier to see what cancels out and what does not cancel out. So we have b squareds canceling, we have k squareds canceling, we have a squareds canceling, we have the minus 2ak canceling, and it seems as if that is it. So we can rewrite this and we get on the left side negative 8a plus 16 plus 8k equals negative 6b plus 9. And I'm going to write this as a y equals mx plus b form, or technically b equals ma plus the y-intercept in this case. So we are going to get that b is equal to 4/3 a minus 8k plus 7 over 6. Right, and you get this from taking the 9, putting it on this side, and then dividing everything by negative 6 to get b isolated. So negative 8a divided by negative 6 gives us 4/3 a, and then if you take the 7 plus 8k, which you get from moving the 9 to this side, you get 7 plus 8k, or 8k plus 7, and then divided by negative 6, you get this. So this is our line equation. So the second equation is a line. Okay. And so we want to find when this system has exactly one complex solution z. Well, when will a line and a circle meet at exactly one point? That's essentially what this problem is asking us now. Well, we know that this happens only at a tangent. Not sure why this isn't working. Okay. Okay. Well, it's fine. We'll just stick to it. All right. So the line and the circle are going to meet at exactly one point, and we know that the slope of the line is 4/3. So using that, we can make like a rough estimate of how it should look. I think it's gonna look like maybe like this, and then the other line will be like this, maybe. And these obviously are not parallel because of my drawing, but in reality, they should be. Okay, so going back to this, well, we know that the radius of the circle is 5 due to this equation over here. And we know that the center is 25 comma 20. Okay, and then we also know that the slope of these lines are both 4/3, which means that the slope of this diameter, the diameter that intersects or that is perpendicular to the tangent lines, has to be the opposite reciprocal of 4/3, which is negative 3/4. So if this has a slope of negative 3/4, then we can say that this can be 3x in terms of distance, and this can be 4x in terms of distance. Negative 3x over 4x, same as negative 3 over 4, which is the slope. And then obviously this is a right triangle over here. So it's clear that x equals 1 to make this a 3, 4, 5 right triangle. So we clearly should have that this distance is 3, this distance is 4. And so we're able to tell the points of tangency to the circle. And again, I'll write that down here to the side. We know that the slope of the line slope is 4/3. So therefore the slope of the diameter perpendicular to the tangent lines must be the opposite reciprocal, or -3/4. So that's how we figured that out. And so that means that, well, if we go 4 to the left, 3 up, we're going to end up with this point being 21, comma 23. And if we go 4 to the right, same thing here. This is 4, this is 3. 4 to the right, 3 down, we get 29, comma 17 as a point. Okay, that looks good. Let's work on this now. So these are our two different points, and these will actually yield us two different values of k, which we add up to get our answer. So let's consider this value of k first, 21, comma 23. Well, sorry, not value of k, the value of coordinates at which the both equations are having one solution. So we can plug this in back to either of our equations, really. Um, So we have to plug it in back to this one because this is the only one in which k is there, and we have to solve for k. So plugging in 21, comma 23, a comma b back into this equation, we get 23 equals 4/3 times 21 minus 8k plus 7 over 6. And this clearly is equal to 28. So we have that -5 is equal to -8k plus 7 over 6. And then the negatives cancel. 6 goes to that side. We get 30 equals 8k plus 7. And this yields a solution of k being 23 over 8. Okay, so that's one possible solution for k. What about the other possible solution for k? So this is one possible. The other possible solution is if we use the point 29, comma 17. So we have 17 equals 4/3 times 29 minus 8k plus 7 over 6. Okay. Um, 29 times 4 is equal to, I believe, 116. 116 over 3. We can move that to the left side. So we get 51 over 3 minus 116 over 3 is equal to -65 over 3. So -65 over 3 is equal to -8k plus 7 over 6. And then here we can multiply both sides by -6, and we are going to get positive 130 is equal to 8k plus 7. And then we get another value of k, which is k is equal to 123 over 8. So these are our two different values of k, and this is pretty much all the solutions we have that satisfy this. So now all we have to do is just sum all possible values of k. 23 over 8. I'll actually do this in a different color. So we can add them and then obviously simplify them to lowest terms. So 23 over 8 plus 123 over 8 gives us 146 over 8. And then this simplifies to 73 over 4. Therefore, the sum of the numerator and the denominator is our answer for this problem, 77. So this is the solution to problem number 8 of the 2025 AIME 1 contest. I hope you enjoyed. Please like and subscribe. Thank you.